Okay, so today I'm going to mostly talk about stuff that's in 1.3, although I'm going to talk about some stuff that's just in general to prepare you for homework 2, which is due Thursday. So yeah, I'm going to talk about graph transformations, composite functions, the domain of functions, and then just some random examples that I think might help. And not all of these examples come out of 1.3, but it's to get you ready for the online homework. So first of all, graph transformations. So we've talked about, at this point, several sort of standard graphs. Like we talked about the trig functions and the inverse trig functions and exponential functions and logarithms, and each time I talked about one of these, I drew the graph. So we have this sort of library of standard graphs in our vocabulary at this point. And what the first part of this lecture is about, it's graph transformations. It's how to take a graph that you know and make a small change to it. For example, this first way is if you know what the graph of y equals f of x looks like, and instead of y equals f of x, I want to graph y equals f of x plus c like this. All that does is that takes the original graph and it shifts it up by c units. And then if I were to subtract c instead, that's shifted down by c units. And so this table is kind of a summary of these things. So what we just covered is vertical shifts. It's the shifts that are up and down. There's also shifting left and right. And that's if you have addition or subtraction inside the parentheses. So let me point something out here, because this is the hardest part about this to remember and to get straight. It's a little bit confusing because generally we consider up to be a positive direction and down to be a negative direction. And so then when you look at the first two rules, that kind of makes sense. If I'm doing plus, that's up. If I'm doing minus, that's down. But the next two seem to be a bit opposite, because, so just once again, just as up is considered generally a positive direction and down is negative, if you're talking about horizontal directions, going to the right is generally considered positive, right? I mean, at least when we draw an x-axis and a y-axis, the positive values of x are the values that go to the right, and the negative values are the ones that go to the left. And whenever I draw a number line, the positive values are to the right of the negative values. So then, why does minus go to the right if plus went up? Well, it's annoying, but one way you can do it is to just remember that. Remember that it's the opposite of what you think, but you don't have to do it that way. Here's how I understand it. On these two, the addition or subtraction is happening, I would describe it directly to the x. I'm literally taking, like, the original formula was y equals f of x, and the new formula is literally what I would get if I just took this x and I replaced it with x minus c or x plus c. So the addition or subtraction of c is happening directly to the x. Up here, this one, if I moved the c over, it would say y minus c equals f of x. And so I would be subtracting c directly to the y. See, this looks like addition. It's not happening directly to the x, though, because it's outside of the parentheses. If I wanted to phrase this as happening quote unquote directly to a variable, I would move it over here so that y would be y minus c. And so this subtracting a number directly to y results in a shift up, and subtracting a number directly to the x results in a shift to the right. In other words, the way to understand these two is just that the c moved over, the c is on this side of the equation. That's why this seems to have the opposite of effect of what one might think, is that the c is on this side of the equation instead of that one. It's on the right instead of the left. Anyway, that's how it works. And there's other operations. There's, say, this one. It's a stretch or a shrink vertically by a factor of c. So it's like, it's just like basically taking the graph and stretching it vertically, so it just becomes taller, or shrinking it so it just becomes shorter. If c is larger than 1, you're stretching it. If c is smaller than 1, then you're shrinking it. You can also put the c inside the parentheses, and that's a horizontal stretch or a shrink. And again, these two things have an apparently seemingly confusing thing about them, which is if the c is here, if you're doing a vertical stretch or a shrink, then a value larger than 1 gives you a stretch, and a value smaller than 1 gives you a shrink. Notice that those are opposite here. C smaller than 1 is a stretch, and c larger than 1 is a shrink. And that's for basically a similar reason. It's because this c that I'm multiplying here, if I were to divide this, it's like y over c equals f of x. So the effect is the opposite of what it might appear to be if you don't realize that. Just two more. There's the reflections. If you put a negative sign in front of the f of x, that's a reflection over the x-axis. In other words, that turns the graph upside down. If you put the negative inside with the x, that's a reflection over the y-axis. In other words, it's what I would describe as backwards. So you take the graph and you basically just turn it like that. Okay, so let's do an example where I sketch a graph of something. And this is like I was describing. I'm going to take a basic function that I know the graph of. And when we say sketch, I just mean draw a basic picture. I'm not going for a huge amount of detail here, but to me, the important parts of this graph are that it has a vertical asymptote here. It goes through this point. This is the point 1, 0, and it just sort of goes like that. But that's not the one I want the graph of course, right? What I really want is this. So how is this different? Well, in a couple of ways. I got the -2 here and the +3 here. And I don't have to do this all at once. I can take care of one thing at a time. So maybe next I'll just graph this one. I won't have the +3. I'll do, of course, I need the +3 in the very end, but I don't have to do that just yet. What does this do? This, since the -2 is in parentheses, this is a shift to the right by c. So the vertical asymptote, instead of being here, it's going to be 2 units to the right. So here. And instead of going through this point, it's going to go through 3, 0. So here. And then it just kind of goes like this. Yeah. All right, now finally, let's put with the +3. What's that do? It just shifts everything 3 units up, right? That's like this one. I'm adding 3 and it's outside the parentheses. So I'm going to take the graph that I just had and shift everything about this up 3 units. So the vertical asymptote is still right where it is. If I shift it up 3 units, it's still the same vertical line, right? This point, instead of being at 3, 0, it's going to go up 3 units. So 3, 3. And then my graph is going to have this vertical asymptote. It's going to go through this point, and it's going to sort of have this shape. So something like this. Yeah. Let's do another one. So what I recognize about this is I see a function that I know. I see sine. So I'm going to start with just your basic sine graph. And of course, we know this goes forever. So something like this. Now, let me start dealing with these differences here. Maybe the first thing I'll do is talk about this 2. What does this 2 do? It's a 2, and it's in parentheses with the x, like this. So this is a shrink, because 2 is larger than 1. It's a shrink horizontally by a factor of 2. So what does that look like? It looks like this, except everything is squished by a factor of 2, right? So for example, the original period of sine is 2 pi. I go from here to here, and I'm back where I started. It just repeats this, and the distance from here to here is 2 pi. If I were to squish it by a factor of 2, then it's, instead of 2 pi, it's just going to be pi. And this pi, where it like this pi is like the end of this upward hump. Like sine starts with this upward hump, and then there's a downward hump. So this pi is now going to be pi over 2, and this 2 pi is now going to be pi, and that's going to be 1 period of sine. So there's an upward hump that ends here and a downward hump that ends here, and other than it, like, it just keeps going like that. Yeah. So that's y equals sine of 2x. But that's still not what we want. There's 2 more changes. There's this negative sign, so maybe I'll deal with that next. What does a negative in front of the function do? Well, it's like this. It's a reflection over the x-axis, so it's upside down. So I take my previous graph and I flip it like this, upside down. In other words, this graph, it has an upward hump between 0 and pi over 2. My new graph is going to have a downward hump between 0 and pi over 2. And then this downward hump is going to become an upward hump. And I'll just kind of, unfortunately, my graph went through where I wrote pi over 2, but, and of course this goes forever, right? Finally, okay, I left myself enough space here. I just have to deal with this plus 1. That's the last thing. So this plus 1, as we know, since this is a plus 1 outside of the parentheses, this is going to shift everything up by 1. So basically, the range of this function is from -1 to 1, and everything is going to shift up by 1. So now the very bottom is going to be at 0, and the very top is going to be at 2. So this point is just 0, 0. That's going to correspond to this point now because it's shifted up by 1. And then I have a downward hump between 0 and pi over 2. And the very low point is now going to be 0. So, okay, so let me draw that. I have, starting from here, I have a downward hump. The low point is 0. And then I'm back here at pi over 2. And then there's an upward hump, and the very high point is 2, and then I'm back here by pi. And then it just repeats this, up and down, up and down. So you don't have to be a great artist to do this. Of course, I'm not, but you do need to get the general shape of the graph. So these pictures are good enough for me. Yeah, so then let's talk about composite functions and their domains. So here I have an f of x and a g of x, and I want to find f of g of x and its domain. So first of all, I don't even like writing it this way, f of g of x. To me, this is a slightly weird way of writing it. I like writing it this way. What this means, of course, is that I'm going to take g of x and plug it into f of x. So watch what I do. I'm sort of writing down like a prototype of f of x, except instead of the letter x, I'm just leaving this a blank. What goes in the blank is g of x, so it's this. So that's f of g of x. And we were also asked to find its domain. So to find the domain of such a thing, you really just have to look for where the problems might be. And we went over our list of basic functions. You know, and once again, it's like algebraic functions, trig functions, exponential functions, trig and inverse trig. And I went over the domain of each kind of function. And so we have this mental list of things that we just can't do, things that aren't in the domain of the function in question. And these are things like dividing by 0, These are things like doing the logarithm of 0 or the logarithm of a negative number. Certain trig functions have domain restrictions, like you can't do the tangent of whatever you want. There's certain numbers you can't do the tangent of. There's certain numbers you can't do inverse trig functions of, like the domain of arcsine is from -1 to 1. But instead of going over this long list, why don't we just look at this and see what jumps out at us? Because I don't see any inverse trig functions. I don't see any trig functions at all. I don't see any logarithms. So I'm looking at this function. I'm not worried about any of those things. What am I worried about? Well, I see e to the x, and if you recall, you can do e to whatever power you want. E to the x has a domain of all real numbers. The other thing I notice is that there's division. That's what I am most concerned about this. Whenever I see division, I need to make sure I'm not dividing by 0. So I'm just writing down these phrases just because you need to look at this and think why might I have a problem with the domain? Why might I not be able to plug in a certain number into this function? And you should go through the mental list, and division by 0 should be one of the first things you look for. Division by 0 is a very common domain issue. So let's just deal with it. So this is what we want to not happen. So if we set it equal to 0 and find out what values of x make that happen, then these are the values of x that are not in the domain. So I'm going to solve this. Subtract 1. And I'm allowed to do the natural log of both sides. But now I find that I'm allowed to and I'm not, because as it turns out, doing the natural log of both sides means that I'm doing the natural log of -1. This is a true statement, but this final statement is nonsense. What this means is that there's no solution. The natural log of -1 doesn't count as a solution. You can't do the natural log of -1. So what does that mean? That means that this thing that we were worried about dividing by 0, that actually never happens. There's no value of x that would cause us to divide by 0 here. So even though we were worried about that, we checked it out and it was fine. So the domain is all real numbers. We can write it like that, or in the online homework, they like interval notation, so you can write this as -∞ to infinity. By the way, in interval notation, -∞ and infinity would always get parentheses. I would never write an interval with a bracket. Infinity and -∞ are not numbers. They can't be included in an interval, and a parentheses means not included. A bracket would mean included, and that's why a bracket wouldn't make any sense. So, yeah. What else have we got here? G of f of x. And just to remind you, f of x is this, g of x is this. So if I'm going to do g of f of x, and once again, I prefer to write it this way. Last time we did f of g, and that meant that I wrote down f, but when I was about to write the letter x, instead of x, I wrote this. Now I'm going to do this kind of the other way around. I'm going to start writing the formula for g. So the formula for g is e to the x. But when I find myself about to write an x, instead of an x, I'm going to write f of x. So this is e to the power 1 over 1 plus x. This thing is all the power that's on top of the e. So this is g of f of x. Let's talk about the domain. So what could the possible domain problems be? And again, let me say some obvious things. I don't see any logarithms or inverse trig functions or trig functions. I see an exponential, but I can do e to whatever power I want. So there's no danger that I would take e to a power and that would cause a problem. I also see division, once again. And again, like I'm kind of going backwards just because I want to make a show of saying all the obvious things, but actually one of the first things you should check for is division. I might be dividing by 0 here. So I should check that I'm not dividing by 0. So I'm going to write down this equation, and basically this is what I want not to happen. So if I solve this, then any solution for x is not in the domain, because these are the values that cause me to divide by 0. And this is very easy to solve. So this time I do get a solution. So this value of x is not in the domain. This is the only value of x that is not in the domain because, once again, there's nothing else that would cause a domain restriction of this. There's no logarithms, there's no inverse trig functions, there's nothing else. The only thing that jumps out at us is this division by 0. So the domain is, it's all real numbers except x equals -1. Here's a way to write that. This is the interval from -infinity to -1. This would always have parentheses. This has parentheses just because we don't want to include -1. And then this represents all the numbers that are smaller than -1. We also want all the numbers that are bigger than -1, and those are here. Okay, let's do a couple more. So let's do f of f. So once again, this was f. And remember, and I'm about to do f of f. So, and this goes, I mean, it's a little bit of a, you know, it gets confusing when you're doing the same function of itself, like f of f or g of g. But I do the same thing. So I'm going to start by writing down the formula for f. And what I would be about to write here is an x. And instead of an x, I'm going to write this. So it looks weird, but it is what it is. And why don't we try to simplify this? So one thing that you will learn about me, and this is not just unique to me, but I don't like fractions inside of fractions. Frankly, I'm not a big fan of fractions at all, but especially fractions that have fractions inside of them really bothers me. So what do I mean by a fraction with a fraction inside of it? So I mean, well, something like this. So this is a fraction that has like this fraction bar, and the numerator is just 1. I'm fine with the numerator. The numerator is just 1, and I would not say that 1 is a fraction. The denominator is the one I have a problem with. The denominator of this fraction, so if I can just, the denominator is this. And that has a fraction inside of it, this fraction. So that's what I mean when I say a fraction inside of a fraction. So I don't like that. What am I going to do? Whoops. I am going to, actually, let me just, here's what I'll do. I just rewrote it. I'm going to multiply the top and the bottom by something that will kill this denominator. This is the fraction inside of my fraction, and that's what I don't like. Its denominator is 1 plus x. So I'm going to multiply the top and the bottom by that. What do I get? I get, so the top is easy. The top is just 1 times 1 plus x, so that's 1 plus x. What about the bottom? Let me put parentheses around the bottom because I have to be careful to distribute here, right? When I multiply this through, I have to take this 1 plus x, I have to multiply it by this part and also by the 1. I'm emphasizing this because it's easy to make a mistake. It's easy to make the following mistake. I'll just cross this off, and then say, well, 1 plus 1 is 2, so the bottom is now just 2. That would be a mistake. Let me show you how to do this properly. Of course, there is some cancellation, and that's the point of this. That's why we're doing this. When I do this part times this part, 1 plus x cancels with 1 plus x, and I just get the 1. However, I still have to distribute this to this, and so I'm not going to get a 1 here. That would be the mistake, is to just write a 1 here. This times this is not 1, it's 1 plus x. So I get 1 plus x over 2 plus x. So now that we have that, let's talk about the domain. And this one has a little trick to it. And actually, there's a reason why I'm doing this one. And actually, after we do this one, maybe you will think that we should have been more careful on the previous examples. And I'll talk about that too. But first of all, let's talk about the obvious thing about the domain. If I just look at this formula, something jumps out at me, and I'll say the obvious things again. I don't see any logarithms, any inverse trig functions, any exponentials, anything like that. I do see division, so I'm worried about dividing by 0. The value of x that would cause me to divide by 0 is -2, of course. So x can't be -2. But there's more. And that's the thing about domains of composite functions. In order to be in the domain of a composite function, x has to be in the domain of the inside function. And if you're doing f of, well, yeah, maybe that's a, yeah, unfortunately, f of f is a unfortunate example because the inside function is f and the outside function is also f. So when I say the inside function, I mean like the second one. It's like, yeah. Of course, the other way of writing this is f of x. So the inside one is the inside one like this. Okay, so once again, in order to be in the domain of a composite function, x must be in the domain of the inside function. F is this function, 1 over 1 plus x, and the domain of this is really simple. Once again, the only thing to really worry about here is dividing by 0, and the value of x that would cause that is x equals -1. So x also can't be -1. Okay, but that's it. And I'll put my answer in interval notation. So there's the interval from -infinity to -2. Then there's the interval from -2 to -1. And then there's the interval from -1 to infinity. That's the domain. And by the way, the examples that we did before are okay. We can go back and check them. For part B, the thing that we should check if we're checking this, which we should, is that x is in the domain of the inside function. The inside function is f, and as we just talked about, the domain of f is everything except -1.